Very good morning, dear friends. Myself, Dr. Vikrant Sudhakar Payekar. I am working as assistant professor in Gokhale Education Society's Arts, Commerce and Science College, Jawahar, Palghar. Welcome on the lecture series on a topic natural product. This particular topic is very important in view of the natural compounds which are isolated from the nature. So this is the first session. In this particular session, we are going to see the introduction about terpenoids and citral. Before that, let us have a overlook about the introductory part related with the natural products. As the word reflects, natural. So basically, these are the natural products are compound or substances which are produced by living organism or organic compounds which are obtained from natural sources such as plant as well as animal. So basically natural products are the organic compounds which are basically obtained from the nature. From the nature they might be obtained from the plant source or from animal source. So in the nature we have to isolate them. First we have to isolate them from the natural sources. These sources may be, let us say, plant or animal. And after the isolation, we have to isolate the important ingredient, or we can say the isolated compound, which must be purified by the process like solvent extraction, fractional distillation, crystallization, sublimation, or etc. So these are the processes we have to carry out in order to purify that particular natural product. So first thing is isolation, and next one is purification. If we see natural products, basically natural products are the compound which basically contain the families from the terpenoids, alkaloids, steroids, carbohydrates, proteins and hormones. So these are the families which are the part of the natural product. As we know that natural products are extensively used because of their wide applications. If you see their application, they can be widely used in the field of food industry, medicines. This is one of the important part in the flavoring, in perfumery industry, plastic and paints. So these are such a wide areas where natural products are extensively used because of their good application properties. So basically in this particular part we will see some of the families or classes of natural product from the terpenes, alkaloids and hormones. These are the only three parts we are going to see in this particular session only. So basically let us see first what are terpenoids. As I already mentioned, terpenoids are the natural compound. So basically terpenes are the group of compounds which are occurring in many essential oils, soaps and tissue which are from the plant kingdom. So if we see terpenoids are the natural compound which basically has the unsaturated hydrocarbon having general formula C5H8N. So we have to remember the terpenes are having general formula C5H8N. This N is variable. It is having number from 2 to onwards. Terpenoids are also called as isoprenoids. Why they are called as isoprenoids? Because they contain the isoprene unit. What is the isoprene unit? Basically, isoprene unit is nothing but 2-methyl butadiene part. So this is a isoprene. So that's why they are also being called as a isoprenide. I will repeat again. Terpenoids or terpenes are also called as a isoprenide because of the presence of isoprene unit in them. As we have already talked, they are having the general formula C5H8N and they are classified on the basis of value of N. So whatever the value of this particular N, based upon that these terpenes are classified into subclasses. Terpenoids include addition of hydrocarbons or other derivatives such as aldehydes and ketones. As we can see from this particular general formula, they contain only carbon and hydrogen, but along with the carbon and hydrogen they also contain some oxygenated derivatives. These derivatives may be, let us say, alcohols, aldehydes and ketones. So these are the examples of the terpenoids: citral, alpha-pinene, camphor. I have taken selective because these are the names which you have heard in general application. So remember, citral, alpha-pinene and camphor, these are the classes of examples of the terpenoids. Now let us see the classification of terpenoids. As we have seen, they contain the isoprene unit, and isoprene unit is nothing but 2-methyl butadiene part. So their classification is based upon the value of N. So based upon the value of N, they are classified into subtypes. So let us say what are the different classes of terpenoids. If the single unit is there, it is being isoprene unit. If the value of N here is 2, that molecular formula will become C10H6, that H16. So that class will be monoterpene. Okay. Suppose when the value of N is 2, that class will be monoterpene. Having example, let us say citral and alpha-pinene. If the value of N is 3, it is being called as a sesquiterpene. The molecular formula will change according to that, C15H24. If it is 4, diterpene. If it is a N value is 5, then it will be called as a sesquiterpene, C25H40. Then value of N is 6, triprene. So based upon that, the value of, as the value of N increases, that particular class also have the different nomenclature. So we have to remember the basic classification of terpenoids. Remember, when the value of N, this particular value of N corresponds to N, so that particular compound get converted into polymeric example. So that is called as a polyterpene. And natural rubber is the very good example of polyterpene class. Remember, when the value of N is equal to N, that particular class is polyterpene, and that will be example natural rubber. So let us see what is the structure of isoprene unit. As we know that this is a single unit which is present in the terpenoids. So here you can see isoprene, it is having the structure name 2-methyl butadiene. So basically it is a butadiene species having branched carbon. The numbering must start from here, 1 2 3 4. The numbering is wrong here, 1 2 3 4. So this particular structure we can write on this way also, CH2 double bond CH CH3. So this is a side chain, and this is a red color shown, it is the main branch chain. So if we see example of citral, as we know that citral is having value of N equal to 2, so it is a monoterpene. So this is a structure of citral. So basically we have to remember citral is a acyclic monoterpenoid. Acyclic means what? This compound is not a cyclic one. Acyclic means it is an open chain compound, and it is having the class aldehyde. So this is a structure. If you see here, these are the carbon skeleton. Then this is a structure of camphor. This is a bicyclic compound. We have already seen the nomenclature of this particular compound. Camphor, alpha-pinene are the monoterpenoid. So let us remember the structure of citral and camphor. So here we are going to see the isoprene rule, because as we know that isoprenes are the compounds, basically they are obtained by the distillation of terpenoids. So they are the we can say one of the product which are obtained from the terpenoids. In 1887, the scientist Wallach, it suggests that the carbon skeleton of all the naturally occurring terpenes are built up of isoprene unit. This is the first time the scientist has mentioned that the naturally terpenes contain the class of isoprene unit, which is known as isoprene rule, and it can help to elucidate the structure of simple complex terpenoid. So basically first time we come to know that the terpenoid contains isoprene unit. So we have already seen this is the structure of isoprene. So if we see, it is a carbon skeleton in this way. Here you can see this particular part is branch and this is a linear one. So we have to remember this is a basic building block which is present in the terpenoids. Then spatial isoprene unit. This particular spatial isoprene unit is given by the scientists in gold. Here come with some different phenomena which help to explain the basic skeleton of terpenoids. So basically the branch end of the isoprene unit is considered as a head and other end as a tail. So according to this particular rule, the isoprene unit are joined together in head to tail manner. So this is known as spatial isoprene unit. So this particular rule is having some different nomenclature, that is also being called as a head to tail manner structural arrangement. So see, let us see what is head to tail. So we can say this is a one isoprene unit and this is a second isoprene unit. So basically we can say this is a monoterpenoids. So basically if we have such a skeleton, then this is a branched end. Here you can see one of the carbon is branch. So this particular carbon isoprene unit in the isoprene unit is considered as a head, while this particular carbon is considered as a tail. In second unit also we have head, we have tail. So remember, so isoprene or spatial isoprene unit is one which explain the how the isoprene unit are joined together into head to tail manner. So here this is a structure. So this is the first structure. This is a this is the first isoprene unit. This is the second isoprene unit. So this is the head. This is a tail. This is again head. This carbon is tail. So we have to remember the isoprene rule which explain the carbon skeleton of terpenes. Now we are going to see the next class, that is citral. As we know that citral is most abundant in naturally occurring acyclic terpenoid. We have to remember citral is acyclic terpenoid. Its chief source is the lemongrass oil and it is used as a flavoring agent for soap and cosmetic and perfumes. If you see, it is a colorless liquid having smell of lemon and it is optically inactive. Citral is basically we can see in the nature it is obtained from the lemongrass oil. If you distill or extract that particular lemongrass oil, you will get the citral. So this is basically a liquid having smell of lemon. If you see its molecular formula, it is C10H16O. In the last slide only we have seen citral. What is the structure of citral? This is the structure of citral having molecular formula C10H16O. So we have to remember citral is the acyclic monoterpenoid. Okay, it is having C10 means N equal to 2. So basically it is a aldehyde. Okay, and containing 2 carbon-carbon double bond. If we see its carbon skeleton, it is in this way. So this is a head. Then this will be tail, this will be again head, this is a tail. So this is skeleton which is connected by head to tail mechanism. So in order to find or to determine the structure of citral which is obtained from the nature, so what are the different structural determination we have to confirm. ये जो structure है उसमें कौन कौन से structural determination we have to find out. हम जो ये जब स्ट्रक्चर देखते हैं तो उसमें क्या नज़र आता है, देयर आर 2 डबल बॉन्ड्स. ओके, सो वी हैव टू प्रूव दैट देयर आर प्रेजेंस ऑफ 2 olefinic double bonds. Then this particular compound is having carbonyl group, that we have to prove. Then that particular carbonyl group is having aldehyde functionality. And if you see clearly, this is the first carbon, this is alpha, this is beta, or second and third. So we have to consider this particular citral is having presence of alpha beta unsaturated aldehyde. So in order to determine the structure, we have to at least show the presence of these 4 main characteristic functionality which is present in the structure of citral. Many times there is a question, use the structural elucidation of citral. So how do we have to prove? First, we have to prove with the help of chemical test that there are presence of two olefinic double bonds. How we can prove the presence of unsaturation? So reaction with the unsaturation state with the bromine liquid. Okay, so citral reacts with the bromine to give tetrabromo derivatives. So what will happen when citral will react with the bromine? It will form tetrabromo. The four bromine molecules will get added across carbon carbon double bonds, and it will be obtained as a tetrabromo derivative. So we have to take two bromine molecules. So once this particular addition is done, we can say there is a presence of two double bonds in the citral molecule. Then next is presence of carbonyl group. This test we also carried out in when we perform organic qualitative analysis inside the laboratory. If the compound is given, let us say aldehyde or ketone, so we carry out 2,4-DNP test. Okay, what is 2,4-DNP? 2,4-dinitrophenylhydrazine. So as we know that when carbonyl compounds reacts with the hydroxylamine or phenylhydrazine, they form the oxime or phenylhydrazine. So that proves the presence of carbonyl group. This is a reaction. If your compound is containing carbonyl group, we react with the hydroxylamine, it will form the oxime. So it is precipitated in the form of orange crystal. If you take DNP, 2,4-dinitrophenylhydrazine, if you react with the carbonyl compound, that may be, let us say, aldehyde or ketone. So on dehydration, it will form phenylhydrazone. So it will precipitate. So and that proves the presence of carbonyl group. So this particular test is obtained for the citral, and that's why we can say a citral contains carbonyl group. Then next, once your carbonyl group is fixed, we have to prove whether it is aldehyde or ketone or any other. So that's why we have to perform the failing solution test. This particular is the confirmatory test. This also we carried out when we carry out the organic qualitative analysis. So failing solution test indicate the presence of aldehyde group, as during the test the reduction of primary alcohol, that is geranol, by sodium amalgam, and it is being oxidized to geranic acid to form the silver oxide. So this particular test is given. So here we can clearly prove that that particular carbonyl group is in the form of aldehyde. So this particular failing solution test is help to determine that the citral contain aldehyde functionality. Then the presence of alpha beta unsaturated aldehyde. For that we have to perform the test where 2 moles of sodium bisulfate we have to use, and this particular test, if we carry out, we get the bisulfate salt. So this is a chemical reaction which obtain, and this particular bisulfate salt is obtained, and which is a characteristic reaction for determination of alpha beta unsaturated compound. And here we can easily say, if we take the UV spectrum of citral, so we obtain that here is the presence of unsaturation. So here must be the N to pi star and pi to pi star excitation must takes place, and as a result of that you will get the lambda max at 235 nanometer, and which indicates that there is a presence of conjugated aldehyde. Conjugated means what? Here you can see this is a conjugated. The two carbon carbon double bonds are separated by single bond. So the lambda max at 235 nanometer is helpful to understand the given compound is containing conjugation. Then if we carry out the reaction of citral with K2CO3, that is hydrolysis, so it is being reduced into methyl heptanone and acetaldehyde. So what is methyl heptanone? So this is structure. Okay, so here you can see this is now being converted into ketone. So remember, methyl heptanone, last word ONE, it indicates that this is a compound which is from the ketone family. The two carbons are being eliminated, and as a result of that we get the formation of methyl heptanone. So these are the structural determination tests which helpful in order to determine that your compound contain carbon carbon double bond, then carbonyl functionality, then presence of alpha beta unsaturated carbon. So these are the tests which will determine that your citral contains structure which is having aldehyde as a functionality. So these are the part which will we can see in case of the terpenoids and citral. So go through this particular part. It will helpful to understand the basic structures related with the terpenoids and citral. Thank you very much. See you in the next session with next term related with the natural product.